Okay, so this is the derivation of our thrust equation. So we start out with the thrust being the difference between the mass flow rate and the velocity going in and out, and there's no velocity of water going in, so this goes to 0. Mass flow rate is represented by the density times the volume flow rate. The volume flow rate is just the velocity times area. So we move to Bernoulli's equation to get expression for the velocity. So it's the pressure 1 times the velocity in again is 0, so this term goes to 0. So we're left with the difference in pressures and then the difference in the gravitational potential energy. And the difference in gravitational potential energy is negligible compared to the difference in pressures, just because it's a very small bottle. We're not talking about the bottle itself moving, but the water inside of it. So here we get our expression for velocity, plug that into our thrust along with the mass flow rate, and we get an expression that depends on pressure as a function of time. To get this, we use adiabatic expansion. We can assume it's adiabatic because it happens so quickly. So using this equation relating the pressures and volumes, we get an expression for the pressure as a function of time in terms of the velocity, the volume. So we plug that back in to our thrust, and we get thrust as a function of volume, which is a function of time.
The key to getting the rocket to go in the designated direction is to have the center of mass be in front or closer to the nose than the center of pressure, since the moments of the drag stabilize the rocket in the correct trajectory. So the first thing I did was find the center of mass, which you could basically do by placing the rocket on a flat rod or pen. I chose my finger, and essentially wherever you can place your finger along the long side of the rocket is without having it tip over to one side is where the center of mass is. And the center of pressure I determined by finding the centroid of a 2D projection of the rocket. And we can do this by splitting up the rocket's projection into different shapes, like simple shapes like ovals and parallelograms, and then you can use centroid equations to find where that is. And essentially I found that the center of mass is about 3/5 of the height of the rocket, and the center of pressure was behind it at 2/5 of the height of the rocket. And we were able to do this because we taped a piece of stock metal to the nose. And the general shape of the rocket, the nose should be dome-shaped, essentially, if it's slower than the speed of sound. And it's only cone-shaped when it's going at supersonic speeds. And the diameter of the rocket, typically a smaller diameter produces less drag, but overall we decided to go with the bottle because that was the only resource we had. And for the fins of the rocket, we chose larger fins so that it would create a greater area in the back and pull the center of pressure towards the back of the rocket. and typically fins are only minimally producing lift. So the parallelogram shape was really just to induce some drag and to be able to control our rocket.
The motion of the rocket can be divided into 3 stages. First, the thrust stage, where water is leaving the rocket and there's a force pushing it forward. Next, the post-thrust ascending phase, where the rocket is still moving upward, but there's no water left in the bottle. Next, the post-thrust descending phase, where the rocket is moving downwards again. In the thrust phase, given the thrust profile and an equation for how the mass of the bottle varies with time, it is possible to find equations for the acceleration in the x and y directions of the bottle by analyzing the free body diagram as shown. Similarly, we could analyze the accelerations in the post-thrust and thrust ascending phase as well as the post-thrust descending phase. The drag force was found using the drag equation, and the drag coefficient was estimated to be 0.82, which is the drag coefficient of a long cylinder. The area of the ball rocket was estimated to be 0.005 meters square. The velocity and displacement could then be measured using the equations as shown, with dt being a small increment in time. These equations, along with the equations for the thrust and mass, were put into while loops with small increments in time to give us the final x displacement. For the conditions given to us on testing day, we found for the
So in addition to our simulation, we did a lot of testing at a fixed angle of 45 degrees at varying pressures to compare to our simulation. We did testing varying the pressure until we had a sufficient range of distances from about 30 to 200 feet, and we figured that on demo day that our target distance would be somewhere in that range. We found that pressure and distance had a linear relationship, so we fit a linear curve to this data. On testing day, the target distance of 70 feet was given. Using this relationship, we got that the pressure should be about 34.5 psi. And to check this with our simulation, since our simulation takes in a pressure and gives a distance, not the other way around, we couldn't plug in the 70 feet, so we plugged in the 34.5 and found that our simulation gave an output of about 120 feet instead of 70. So we decided to trust our data more than the simulation because there are a lot of assumptions made in our simulation that we'll talk about a bit later. So using the 34.5 psi, our rocket went about 70 feet, but off target a little bit. So it landed 10 feet away from the target at a little bit of an angle. So our demo day results deviated from our expectation for 3 main reasons. So we launched the rocket at 45 degrees with 34.5 psi and expected it to go 70 feet. It went a little bit to the left of the target and a little bit short. One big reason for that was that there was wind that was going in just about that direction, like towards us and a little bit to the left. So that definitely had at least some effect on its landing position. Additionally, our three variables that we control: the angle that the rocket is launched from, the volume of water that we place inside, and the pressure, are all pretty hard to get exact given our equipment. Just using like milliliter markers on a water bottle, the protractor, and the bike pump. None of those could have been exactly perfect. Additionally, there's a variation in any given testing, even with all the conditions held constant because of the asymmetry of our rocket. Our fins, while they're close to being symmetrical, were not quite. So this caused a rotation, and also the mass we taped to the top was not perfectly symmetrical. So any given orientation, or the orientation that we fixed to the of the rocket that we fixed to the launcher, any change in that orientation would result in a change in landing spot.
The predictions of our calculations were pretty far off from our experimental results. This is the reason we used our experimental data to find the appropriate angle and pressure at which we would launch on testing day. Given our parameters, if we'd launched it according to our calculations, it would have gone 110 feet, 120 feet, but it did not. Two main reasons for this deviation are assumptions that we made in our calculations. One assumption was that the angle of the rocket with respect to the horizontal does not change in the thrust phase or the post-thrust ascending phase. It remains the same as the initial launch angle. At its peak, it instantaneously changes angle and is a constant angle below the horizontal during the post-thrust descending phase. This is not true as the angle changes with respect to time. This could have introduced errors into our simulation. Another big assumption was the drag coefficient. It was assumed to be the same as the drag coefficient of a long cylinder. However, our bottle was not a long cylinder. It had a dome-shaped end of our moss, as well as fins at the back, which could have affected the drag coefficient. As a result, our estimation was pretty far off. Additionally, the rocket did not stay in the same plane, and the calculations assumed that it would remain in one plane. Some of the ways we can improve our results are firstly by making more accurate measurements of our initial parameters. For example, the volume of water could have been measured more accurately, as the millimeter markings on a water bottle are not that accurate. Additionally, the pressure gauge on the bicycle pump could have had a finer gauge, as well as the angles on the protractor. The rocket was not as symmetric as it could have been. We could have made the fins more symmetric and ensured that our mass was exactly at the center of the rocket. With regard to our calculations, we could have changed theta at each iteration as the velocity in the x and y changed. We also could have experimentally determined the drag coefficient instead of assuming it to be that of a long cylinder. These would have made our results more accurate.